Lesson 8.5, using exponential and logarithmic functions. So the last two lessons of this module, 8.5 and 8.6, are a bunch of word puzzles and applications of what you've been applying so far, all this module. Right, so nothing I don't think extraordinarily new, right, just applications. Right? I got a list of applications here. So you'll see a lot of puzzles related to banking, population growth, radioactive decay. Right? I threw on a couple examples myself. Sound intensity, so how many decibels or something, right? That's on a log scale. Technological advancement, for example, Moore's law, right? That could follow an exponential curve, right? And so here's some real life applications, right? And your book likes to focus on these three for a bunch of stories. So yeah, let's dive in and see what we got here. Okay, example one, continuous exponential growth. The table shows the population of Florida in recent years. Right, so 2000, oh, okay, then it jumps all the way to 2015, 16, 17, 19. Okay. We got population in millions. Right, it's hovering around 20 million or so. Right, let's grow a little bit. Because the population is growing as time passes, use the year as the independent variable. Right, so like x could be the year number, and the population is the dependent variable. Find the value of k, Florida's growth rate. Then write an equation that represents the population of Florida 2 years after 2000. Okay? Right, now, there's a couple of ways you can create a growth curve. Okay? So here, oh, right, both of them. Right. So example one. Okay? So growth. Okay. It kind of reminds me of banking, or you guys saw simple interest versus compound interest. So you could have the amount is equal to the initial amount times, and then one plus the growth rate to say however many years have passed on an annualized basis, right? Or you could have continuous, so continuous growth. So that would look more like this: a equals a naught times e to the kt or rt, right? One version of the other, right? These are different type models, but you could adjust them a little bit too, so they fit on top of each other, right? Like this r and this k might be slightly different values, right? Right. So, like in banking, this one was called simple interest. That would be like what refers to R. If you said, "Oh, we're going to offer you like 5% interest," okay? And this one is continuously compounded. Okay. All right, so two little bit different models. Now, it looks like your book is suggesting to use the continuous model. So we're going to use that. Okay, let's try that. All right, now they give you this table right here. All right, so let's plug in the values in Desmos. All right, so type in table, bam, we got a table. Okay, now the year 2000, we're just going to call year zero. And then it jumps 15 years in the future, and then it's 1 year after that. So 16, 17, 18, and 19. Okay, so we got those, yeah, 6 years, 6 years going on. All right, then the population of millions, we got 15.98, 20.21, 20.61, 20.96, 21.24, 21.48. Right? Now, since this is real data, or you can assume this is real data, right? The real world's going to be a little bit messy. It might not land like exactly on a curve, right? But maybe we can model this, right? Now, if you stand back and kind of look at that, right? I was thinking this might be, yeah, okay. Now, usually exponential curves kind of bend up. Yeah, this one looks kind of bendy down. Yeah, that's all right. Well, we'll see what we can do with this. Right, so I'm going to fit it to that model, right? The continuous growth model. So I'll say y subscript one, right, and then tilde, right? So let's come up with some value a, right? Multiply, or well, I'll let Desmos figure out what that is, right? Let's use e to the power of, and then k, and then instead of t, I'll call it x subscript one, so it matches my table, right? So like that. Okay, yeah, okay, that looks pretty good. Yeah, I can go with that. All right, exponential growth curve right, for population of Florida. It's about like that. All right, and then right down here, it'll tell us exactly what A and K are. Yeah, there you go. All right. So A should represent the initial population, or very, very close, right? Yeah. Yeah, so textbook value is 15.98 exactly. Are they giving us a, it's pretty close to that. Okay, so yeah, let's go with that. So I'm gonna write that down on paper. Let's see. So we got population as a function of time equals, I'll just call it a 15.98, and that's millions of people times e to the power of 0.0157 something. And then that'd be 1/years. All right, and then multiply it by t. All right, so we bring this back to what I just wrote. All right, so I copy down. This is kind of getting population as a function of time. Pretty much that curve right there, right, for Florida. All right, what else do they want here? So we got ourselves a model. Since t is the number of years after 2000, okay, so this is your initial population. All right, so let's go here. And okay, all right, okay, this is how many years after. All right, so we got that. All right, but boom. All right. Okay, did they? All right, you know what? Okay. Looks like what they did was they actually picked 2 points on the curve and they just did this manually. I had Desmos do it for all the points in the table. Okay. But here, let me do it kind of the way they did it. Right. We'll see. Right. But they did get pretty much the same K value. Look what they got for K, 0.0156. Right. And Desmos did it, got 0.0157 something. That's like almost the same thing. Anyway. Right. Right. So how'd your book decide to do it? And I used the same model. They said A equals A naught e to the kt. Okay. But they went with the initial population versus population after 19 years. So that's what they did. So for here, they plugged in 21.48. That's millions of people. Million people. The initial, go back to the year 2000, 15.98. Yeah, that's million people. Right, the millions cancel. Then times e to the, now we're going to solve for k, but for these numbers exactly are 19 years apart. So the time would be 19 years. This is years for the 19, right? Right. So here's your zero after 19 years for this population. And so how can you solve for k? And you can use logarithms to solve for k. And then get, well, it's what they got, what Desmos got. Okay. So I'm going to divide over the 1598. Here, let me show you guys algebra. Okay. So millions cancel. Divide by 15.98 over 15.98. So 21.48, 1598. I'm looking at 1.344 something is equal e to the, let's call this 19k. Okay. Now I want to take the natural log of both sides. So natural log of the left side equals natural log of the right side. Okay. And so take natural log answer. So all this comes out to 0.29578 is equal to, right? And all this right here is just 19k. Right? Remember your log rules, right? Okay. Divide both sides by 19. So over 19, let's see if we got the same thing. Yep, that's the same thing. So k equals 0.0156. That's 1/years. With a unit. Okay. Yeah. Right. So same thing your book is saying, and same thing, like to the like 10,000th place that Desmos got. All right. So this one down. All right. Ooh. All right. We got a part B. Predict when the population will reach 25 million people. All right. Well, we got ourselves a nice model right here. It boxed it in before. Let's let the population go to 25 million. Right, so for this, I'll plug in 25. Yeah, it's millions of people. Equals 15.98 millions of people times e to the 0.015. Here, I'll just put 6 because right, that's what we, okay. And let's solve for t, right? So now before we apply the logarithm to solve for k, you got something roughly like this, right? And but you see occupies the same space. It's still up here in the exponent. So we're still going to have to apply a logarithm, an actual logarithm, because we've got a base of e. Okay. So let's divide both sides by 1598. 1598. Okay. So it is 25 or 1598. All right, I'm looking at 0.9387-ish is e to the 0.0156t. All right. Right now, how do you get t out of the exponent? You apply a logarithm. I'm going to apply a natural logarithm because I have a base of e right here. So that'll clean up nicely. All right, natural log answer is this all comes out to it's a negative. Yeah, hold on. Wait, what the heck? That should not. Whoops, I mistyped this. Let me go back. There's 25 over. Right. I knew there's something wrong. That can't be negative. Right. Let me get rid of this. This should have been 1.5645. Okay. We're gonna get back on track. There we go. Right. So this fraction is actually this. Okay. Let's take natural log of that answer. All right. Now we're good. 0.4475 something equals, right, and then this all cleans up. It's just 0.0156t. All right, last step. Divide by the size by this coefficient. Okay, divide by 0.0156. I'm looking at t is approximately 28.7 years. Okay, about 28, 29 years. And this is after the year 2000. Okay, so you could probably say the year 2028, 2029, something like that. Okay. Let's see what Desmos has to say about that. We're going for a population of 25 million, right? Okay. So we could have Desmos solve this too. Right. All I have to do is go down here and say y equals 25, as in 25 million, and see where these intersect. All right. And let's see if it gives us approximately the same answer. That should be real close. Yeah, there you go. About 28, 29, between 28, 29 years later. Yeah. Yeah. So to the nearest year, it's pretty dang close. Okay. You know, we solve it two slightly different ways. Okay. About the same thing. So we got a part C down here. Compare the populations of Florida and California. California's population in 2000 was 33.9 million, and its population growth can be modeled by, oh, and okay, they're giving us the growth function. Determine when Florida's population will surpass California's. Oh, so, all right. So we got a couple of models, one that we found ourselves and also with Desmos. And okay, and we got California's, and they're just giving us that. Okay, so California versus Florida. Okay. Well, we know Florida, which the population is equal to 15.98 million times e to the 0.0156, and then t. T is the number of years that have passed since 2000. Okay. Now, California, the population is, let's see, 33.9 million. Yeah, okay, that was the year 2000. So we got comparing apples to apples here. Times e to the 0.0092t. Okay. All right, so here, before I go plug it and check with math, let's back a big picture here. Yes, yeah, okay. In the year 2000, the population of California is definitely greater than Florida. In fact, it's more than twice as big, isn't it? Right, more than twice as big. Right, 33 compared to 15. Okay. Right, but if you look in the exponent, you see that Florida's population is actually growing faster than California's, right? Which creates this scenario where if you follow these curves out for enough time, eventually Florida is going to surpass California. Right, so I could set these equal to each other and solve for the time exactly. Right now they went with an inequality, which I think also makes sense because we're for greater than. Right. Determine when how they phrase this question will surpass California. And I'm just going to set these equal and solve for the time. Okay. And so when would the populations be the same? Right. So this is equal to this. Okay. How can I solve for t? Well, I'm going to take a natural log of both sides. Let's do natural log of 33.9 e to the 0.0092t is equal to natural log of 15.98 times e to the 0.0156t. Okay. Now the t we're solving for is showing up in two places. Okay, we're about to pull it out. Okay. But I have taken a natural log of see things multiplied together. I should have flashed all these log rules up here before. Okay. But the next rule I'm going to apply is this product property right here. So log of a times b is log a plus log b. I can do that on both sides. So on the left side, it's going to be natural log of 33.9, which is just some number, and then plus, and then natural log of e to the 0.0092t is equal to natural log of 15.98, again, just some number, plus natural log of e to the 0.0156t. Okay, so chasing this t. Okay. I'm going to get a decimal approximation. What is natural log 33.9? Okay. So this right here is the number 3.5234. That's cut off at some point. Okay. This right here simplifies to 0.0092t. Exponents are gone. Equals, what is this right here? 1598. We're looking at 2.7713. And then this again, the exponent goes away, 0.0156 and t. Or the exponent drops down, same level as everyone's like. Now this looks like a standard algebra 1 puzzle. Okay, I got 4 terms, 1, 2, 3, 4. 2 of those are constants, pull those together. 2 of those have the t, pull those together. Let's do that. Okay, so I'm going to subtract over u. Let's get the t on one side at 0.0092t. Minus 0.0092t. Well, I'm at it, I'll subtract this over. Minus 2.7713. Minus 2.7713. Okay. Okay, clean all this up. So 35234 minus 27713. Okay, is right, so all this right here comes out to 0.7521. That's equal to, and over here is a we got 0.0156 minus 0.0092. All right, this right here is 0.0064, and then that's t. T we're solving for. So t right there. Okay. Divide both sides by this coefficient right here. Here, right there. Divide by 0.0064. Divide 0.0064. All right. So 0.7521, 0.0064. I'm looking at the time is approximately, oh, is that right? 117.5 years after the year 2000. So that'd be about the year, what? Year 2117. Here's 0.5, right? Maybe like June or July or something like that, right? Okay. Okay, is that Let's see what your book got. This is an example here. Okay, yeah, they got exactly the same thing. It said after this particular year, the populations are going to pass. There you go. Same thing. Right. Boom, boom, boom. 117 years after the year 2000. All right. Example 2, continuous exponential decay. Ooh, exponential decay. So here's my classic physics example I've been showing you guys. It's like radiometric dating, right? So if you have something that's radioactive, maybe it can have a half-life. Right? And my classic example is carbon-14. Your book does a few examples of that. Right? So 5,700 years, the amount of carbon-14 goes to half of what it originally was. So this time will be 5,700 years for carbon-14 specifically. Different isotopes that are different half-lives. Right? After another 5,700 years, now you get half of that half. After another 5,700 years, you get half of half. Now you're down to an eighth. Okay? Right, so if you're an archaeologist and say you find something with 1/8 of the original carbon-14 that it should have, you know, the 3 half-lives have passed. That's what, like, probably close to between 15 and 20,000 years old, something like that. All right. So what's going on with this coral here? The half-life of a radioactive substance is the time it takes for half of the atoms to disintegrate, yeah, to radioactively decay. The radioactive substance thorium-230 is used to determine the ages of cave formations and coral. Yeah, yeah. So if you ever read an article like, oh, the age of this cave or the age of this coral is however old, right, how do they know that? Well, probably with this thorium-230 isotope. The half-life of thorium-230 is 75,000 in some years. Wow. Okay. So it has half the thorium that it should have, thorium-230. Maybe it's 75,000 years old. Determine the value K for the equation of decay for thorium-230. Okay. This is probably the first part of a multi-part puzzle, I'm thinking. We got to create the equation first before we can apply it. Yeah, and they're prompting the same model that continuous growth and decay model. The only difference between growth and decay with this model is there's a negative exponent. That's all. For decay, there is a negative. So I'll say the amount is equal to the original amount times e to the kt, or at least that's what I have been using. If I run this, I'll get a negative value for k. If you slap your own negative in there, you'll get a positive value, whatever. We got to chase down k. Yes. So they just told us what the half-life is. It's 75,000 some years. So whatever the initial amount that you start with, it becomes half of that original value if I plug in 75,000 years for t. And more precisely, 75,381 years. There we go. Okay. All right, so let's chase down k. Then we'll know exactly how thorium, we'll have an equation for it. So take the natural log of both sides. So natural log of this side equals natural log of this side. All right, the a not cancel, whatever, it's fine. And so natural log of 1/2 is equal to natural log of e to the negative 75381k, which of course is, you know what, here, let me do something a little funny. Guys, natural log of 1/2, isn't that like natural log of 2 to the negative 1? 2 to the negative 1, right? I can pull the negative out using, what rule is it? It's this power property right here. I'm about to do this step right here. It's the same thing as negative natural log of 2. Let me show you guys this trick. Watch this. Natural log 0.5 is negative 0.693 something. If I do negative natural log of 2, it's the exact same decimal, negative 0.693, whatever. Same. Right, so, and then this all here just simplifies to negative 75381 thousand. Okay. Divide both sides by this coefficient. Negative 75381. Negative 7. What did I do? 75381. Okay. See, what is 2 over 75381? I'm looking at a k of e. Now that's a tiny k. 0.00000. Did I get that right? 1, 2, 3, 4, 5 zeros, and then 91, 95, right? Or in fact, it's so tiny, it's probably more efficient to write this in scientific notation. Let me spell that out. Scientific notation, which is just copy the digits. So 9.195, and then we need to restore the decimal place times 10 to the 1, 2, 3, 4, 6, 10 to the negative 6. This would be 1 over years is the unit. Okay, so tiny k value, right? But now that we have that k, we can come up with an equation for this isotope of thorium. Okay? Right, so the amount is equal to the initial amount times e to the negative 9.195 times 10 to the negative 6, and then times however much time has passed. Okay? So that should be the governing equation for thorium 230. Okay. Oh, let's make sure that's what your book got also. Okay, continue on the next page. You should have gotten the same thing. Yeah, exactly. Negative 75381. Well, hold on, that was one of the steps. Here it is, 0.0000092. Okay, yeah, same thing. Okay, so we got what they got. All right, so part B, now we get to apply this equation. How much of a 2-gram sample of thorium-230 should be left after 1,500 years? Now, in the big scheme of things, 1,500 years, I know it seems like a long time ago, it goes back to the Dark Ages, but if the half-life of thorium-230 is 75,000 years, 75,000 compared to like 1,000 something, right? It's probably not going to decrease very much. It's going to be well over 90%, but we'll see exactly. We're going to find out. Okay, so we want, who's gonna, after 1500 years. Okay, so the amount is equal to the initial amount times um, e to the negative 9.195 times 10 to the negative 6. All right. And then for t, we're going to put 1500. Okay. Now the k value is 1 over years and the t is in years. So the units cancel. Plug it on the calculator. Okay. Now notice what I'm really finding here. If I divide over the initial amount, it says a 2-gram sample. Whoops, I should have put that in here. Okay, actually, I forgot they did that. Let's see, 2 grams right here. There we go. Okay. Actually, I just need to plug that in the calculator. That's all we need to do. Okay. Equals. So let's take 2 grams times e to the power of negative 9.195 times 10 to the negative 6, right? And then 1500 years will let go by, right? I'm looking at, no, that's about right. 1.973 grams. Okay, is that what, but yeah, 1.97 grams. Yeah. Same thing. Right. Now, how this would really work in the field, I suppose you're working with thorium or caves or whatever, right? Or corals, right? Is if you expected a sample, like a new sample, to have 2 grams, right? And then you find some more artifact only have 1.97 something grams. Like, okay. So it is a little smaller than maybe like a new sample, right? Yeah. So how much older is it, right? And you could back calculate this 1500 years right here. Right? Yeah. Right, so go back and forth between exponents and logarithms. Yeah, example 3. Oh, here we go. Radiocarbon dating. Yeah. Right, so this is my classic example. Carbon-14 has a half-life. Oh, and you know what? They gave you the K right here. Here, I'll show you guys where this K comes from. Let's get it ourselves. A equals A naught times e to the negative KT we'll be using. Right, so if you start off with any amount, and then you want to get to half of that original amount, then some time has to pass. Right? And for carbon-14, that number happens to be what I showed you a few minutes ago, 5,730 years. And so these will all be in years, so I'll just write the number. Okay? We can solve for k, and they told us what k is going to be, but I'll show you guys that that's true. Okay? So regardless of how much you start with, it doesn't matter. Okay? You start with little, start with a lot. It takes the same time to get to half regardless. So that's the same k. Okay? So take natural log. Natural log of 1/2. Natural log of e to the something. Okay, and then all this simplifies to just negative 573 Divide by this coefficient. Negative 5730. Negative 5730. You guys saw a few minutes ago, natural log over 1/2 is the negative value. It's negative log 2. Negative natural log 2. So natural log 0.5, I was typing in exactly, over negative 573. I'm looking at k equals 0.000121. It's 1 over years. Okay. And that is what your book tells you. Well, they cut it off 1 digit earlier, but it's basically the same thing. Okay, so we got that. We checked the book. Yeah, the book's on track. In 2016, charcoal flakes from the excavation site of an ancient human settlement in Canada were sent for radiocarbon dating. The charcoal flakes were found to contain about 18.6%, as much carbon-14 as they would have originally contained. How old are the charcoal flakes to the nearest year? Ooh. Now, I don't see a solution on this page. It does say continue. Next page, so let's go ahead and solve it. Okay. And then hopefully the answer is on the next page. Okay, so the amount is equal to the initial amount times e to the, okay, got negative 0.000121, and then however much time has passed. Okay. Right now, 18.6%. As a decimal, that's 0.186. Okay. And then of the original amount. So of the original amount equals the original amount times e to the 0.000121t. T is in years. Take the natural log of both sides, natural log, boom, boom. So here, I'll go ahead and get a decimal approximation. All right, this right here, what is natural log of 0.186? That's negative 1.682 is equal to, and then this, of course, simplifies to negative 0.0001212t. Right? Divide coefficient 0.000121, 0.0121. Okay. So, okay, and I've got this in my calculator already. So I'm going to divide by negative 0.000121. Right? So the age of this, what was it? Charcoal flake? Okay. Is, ooh boy, 13,900 years. Okay. Oh, do I really know? It's this last year exactly. No, this is really too much precision. I could say about 13.9 thousand years. Right? That's about it. Right? Maybe even like almost 14,000 years, right? That's after a while. Um, yeah, that should be it. Right? Does this make sense? Does this check out? Well, if I know the half-life of carbon 14 is about 5 to 6 thousand years, right? Okay. So every 5 to 6 thousand years, it's half of what it originally was. Okay. Now, half of a half of a half, what is that? Well, half of half would be 25%. Half, half, half would be down to 12%. 18% is between 12 and 25. So it's like between 2 and 3 half-lives, right? Right. So 2 half-lives is about 11,000 years. Ah, yeah. This definitely looks believable. Yeah, that's right in there, right in there. That's a good thing to do with math and physics, that thought process I just walked you guys through, right? When you get an answer, step back and say, does this make sense? Like in the overall big picture context, can I see the forest for the trees? All right, let's see if that's what they got. Uh, oh, looks like they did not give us the answer, but that's okay because this looks completely reasonable. All right, let's jump into the book puzzles. All right, so I highlighted some of these. First one, we got a table of values, the world population in several years. So 2000, 2001 to 2005. Write an exponential equation to represent the population in billions. Okay, so world population in billions of people. Wait, is this even accurate? I don't know, maybe. After the year 2000. And then predict when the population will reach 7.5 billion people. All right. Now, here, let's try this a couple different ways. Let's go into Desmos and get a table. All right, so I'm going to clear all this out. Clear, clear. Let's clear all this out. All right, we'll start from scratch. Table. Okay. And then I'll treat year 0 as the year 2000. And we'll just point. 1, 2, 3, 4, 5. Okay, 2005 goes to. All right, and the y values, we got 6.124, 6.194, okay, 6.273, 6.352, 6.432, 6.515. Okay. No, there. Yeah, okay. Zoom back here. All right. Yeah, okay, it's gonna look like that. All right. All right, and let's fit this into an exponential growth model. All right, so I'll go y underscore 1, then right arrow key, tilde. Let's go a times e to the power of, in parentheses, let's go k, and then x underscore 1. All right, give us a good exponential model here. All right. All right, so I'm going to write that down. So we got the population is equal to now 6.12. Oh, yeah, okay. 6 point, about 6.12. Okay. And then times e to the, where'd it go? 0.012 I'll call it. Put it off somewhere. And T. All right. All right. So got that. All right. Come on back here. Okay. Nope. Where'd it go? Hold on. Ooh. All right. So this is what we got from Desmos. I'll go ahead and label this one from Desmos. All right. I'm kind of curious to see what I get with a different method. All right, so here, we'll hold this one to the side. Let's say the population is equal to initial population times e to the kt, right? And I'm going to try this method we did earlier, where I'm going to pick 2 years and run the equation. Whoops, population. So let's put initial population as 6.124. These are billions of people. We do continuous growth. Well, we're going to solve for k. Okay. Well, let's let some years go by. Let's say 5 years. Let's take it all the way to the end. So for t, I'll put 5 as in 5 years, and the population is 6.1. Sorry, 6.515. Yeah, billions of people. Right. Right. So solve it this way. So we get. So divide both sides by 6.124. Right. And then take the one step at a time. 6.5156124. Looking at 1.0638847 equals e to the 5k. Take natural log of each side. Natural log answer is, this is 0.06189 equals 5k. Divide both sides by 5. Then getting k is 0.01238. So then this would be the population is equal to 6.124, again, billions of people, times e to the 0.01238 t. Okay? And this is, well, I'll put from table, although I had to pick 2 points and make some simplifying assumptions. Okay? But here, if you compare what I got with this method of picking 2 values from the table to this method where I plugged the entire table into Desmos and had it do the number crunching for me, those are almost exactly the same equation. I mean, it's tiny bit different when they were like way out here on K. So like almost the same thing. All right. So what's the part B here? Use the equation to predict the year that the world population reaches 7.5 billion people. Well, I have two slightly different equations. So let me try each one. Okay, and then I'll say, so population, we're going to target 7.5, that's in 7.5 billion people. Let's try it each way. I'm going to split my paper. Let's do Desmos over here. I'll call this uh, uh, two table values equation on the side. All right, so I've got 2 different equations set up. All right, so on the Desmos side, I get 7.5 equals 6.12 e to the 0.01244. And then we're going to solve for t. Right. And then my own equation that I derived on paper, we're again aiming for 7.5. That's going to take the place of this p. Right. The original value was 6.124, and then e to the 0.01238. And then again, we're solving for t. Okay, so how much time does it take to reach 7.5 billion? Okay. So divide each side by its respective coefficient. All right. Well, yeah. 7.5 over 6.12. This is 1.2255 equals e to 0.01244 t. Okay. Take the natural log of both sides. Natural log. All right, so natural log answer is, right, this all comes out to 0.20334, 0.01244 t. Divide both sides by this coefficient, 0.01244. 0.01244. I'm getting the time is 16.35 years. Okay, that's using the Desmos derived equation. Okay, now this other slightly different equation, probably slightly different, but let's see how close it is to this. So kickstart is here. It's not 5 or 6, 1, 2, 4. All right, so this is 1.2247. Yeah, good. Equals e to the 0.01238 t. A natural log of both sides. So natural log answer is 0.20269 is 0.01238 t. Divide both sides by this coefficient. $16.37 years. Yeah, yeah. Right. So even though the two equations were slightly different from each other, yeah, they're really predicting about the same thing. Right? Takes 16 years and a few months. Yeah, the same answer. Right, population growth. That's the next one we got. Number 5. Half-life. Oh, half-life. Archaeologists uncover an ancient wooden tool. They analyze the tool and find that it has 22% of the carbon-14 compared to what it should have when it was made. Right? So all living organic material has some consistent ratio of carbon-14. Right? But once something dies, then that starts to decay. Right? Now we're down to 22%. Given that they gave us the decay constant of carbon-14 right here, but we derived it earlier today when I was going through the sample. So we got the same number. So they're giving us the correct value, helping us out a little bit here. Okay. So number 5, okay. Carbon-14 half-life equals 5,730 years. Therefore, the K of carbon-14 is 0.00012. Well, that's much the book gives you. Throw in a 1 there. So that'd be 1 over years. Okay? And that would fit into the equation A equals A naught times e to the negative k t. Okay, so including the negative there as it's decay. All right. So now we're down to 22%. So regardless of what A naught is, the original amount, I know that this final A right here is 0.22 times that A naught. That's what 22% of the original is. So equals A naught e to the negative. Okay, and then for K, right there, 0.00012, and then T. And so T is going to be in years. So how many years old is this artifact? Okay, so, okay. Before I go plugging and chugging, here, consider this. 22%. Isn't that a little bit less than a quarter, right? And a quarter is a half of a half. Well, if I know that carbon-14 has a half-life of 5,700 something years, I know that a little more than 2 half-lives have passed. 2 half-lives is about 11,000 something. I'm going to guess roughly 12,000 years old. Okay, so I'm going to make a little prediction here. I haven't solved this yet. Okay, so I'm going to say prediction. We're going to see how close this is. That's 12,000 years old. All right, let's see how close. Okay, so I'll see it right away. It not goes away. I'm going to take the natural log of the left side equals natural log of the right side. So natural log, let me just leave the numbers there. How about that? Equals, and then so it all simplifies to negative 0.00012t. Okay. Divide both sides by the coefficient. 0.00012, 0.00012. Okay, and now it'll tell us t. So let's see. Okay. And it should be pretty close to this. Let's see how close to 12,000 years old it is. I'll pop cloud over here. And so all I have to do is type in this expression right here. I got natural log 0.22 in parentheses, all divided by negative 0.00012. Ah, look at there's 12,618 years. Okay. So about 12,600 years. Right? Do you know that extra 18? It's probably too much precision, but you say about 12,600 years old. Yeah, yeah, that's pretty close to what I was thinking it should be. Pretty good, pretty good. How old's the artifact? It's very old. Hmm. At number nine, depreciation. A global positioning satellite GPS system uses satellite information to locate ground position. Uh, Marshall's surveying firm bought a GPS system for $12,500. Now it's only worth $8,600. The value of the system depreciates at 6.2% annually. How many years ago did he buy the GPS system? Annually. Huh. Okay. I can think of a couple ways to set this up and solve this. Okay. One way is you could set up a continual depreciation. You could force it into this equation. Okay. And okay. I wonder if I should do this two different ways. Let's try this. Let's try this two different ways. Because the other way I'm thinking is sort of like a simple interest uh, uh, application, but of course it would be for depreciation. So let's try. I'll put method one. Okay. Let's use the value is equal to the original value times, right, so I'm going way back, 1 plus r to the t. Okay. Now they told us it depreciates 6.2%, so r is equal to negative 0.062. Think of it that way. Okay. They told us the original value was $12,500. That's dollars. Okay. And now it's only worth $8,600. Okay, so we have a nice equation here. We got 8,600 equals 12,500 times 1 minus 0.062 to the t, and we can solve for t. All right, we can call this method one. Okay. So divide both sides by 12,500. There. Let's get there. So 8,600 over 12,500. So it looks like it's worth about 68.8% of its original value. That's one way to think of it. 0.688 is equal to 1 minus, but I can clean this up too. What is 1 minus 0.062? So this whole thing is like 0.938, right? Or you could say every successive year it's worth 93.8% of what it was the previous year. You have the plus 0.938 to the power of t. Right? Now when I take natural log of both sides, I can take this t in front. So natural log of 0.688 is equal to t times natural log of 0.938. Divide both sides by natural log 0.938. Yeah. That'll tell me this t right here. All right, we're about to find it. What's natural log of 0.688? Throw that some parentheses. Divide by natural log 0.938. I'm looking at 5.84 years ago. Years ago. Okay. And so that's how old the system is. Okay. Okay. Now that was what was called method one. But I'm going to try a different method. Let's see if I can force it into a continually depreciating model. Okay. So let's do, and I should get the same answer. Okay. So method two, let's force this into a equals a naught e to the negative kt. Okay. Now, with this method, we do have to solve for k first. Okay. And it's not going to be exactly, this. It should be a little bit different. Okay. So let me solve this after 1 year, because I know that whatever the original value was, after 1 year, it is only worth this much. Okay, so 0.938 times the original amount. Okay, and that's if I plug in 1 year for t. Right, yeah, it'll go down to 93.8% of its original value, which means I can solve for k. Okay, so let's do natural log of 0.938 equals natural log of e to the negative k. The negative k can come out in front. Natural log of e is, of course, equal to 1. Right? All right, so k is just equal to negative natural log 0.938. Okay, let's see what that is. Negative log 0.938. I'm looking at k is 0.027797. Okay, okay, now that I got k, I can plug that back here, and I can try this a different way. So let me make sure I got that right. Oh, hold on, hold on, hold on. That looks wrong. Sorry, it's not log, it's natural log. Okay, whoops. Let me check that. So you got natural log 0.064005. Let's try that. Okay, there you go. Okay, natural log is 1, 4. Okay. Okay, so with that method, we're gonna say, right, so I'll go back to this model, but now I know the specific present value is $8,600. The original value was $12,500. These are dollars. Okay. Okay. But now I'm using the continual model, okay, which means I need this k value of 0.064005. Okay. Okay. And I'll solve for t this way. Okay. Okay. So same first step, divide this down, 12,500, 12,500. Okay. Okay, so 0.688 equals e to the that. Okay. Take the natural log of both sides. So it's negative 0.373966 equals negative 0.064005. Right. Divide both sides by this coefficient. Okay. I'm getting t equals 5.84 years, like years old. Like I said, years old, years ago, something like that. Right. Right now, so this method was a little bit longer because I had to solve for the k value first, but I could fit it into this continuous model, right? Because it's continuously depreciating. Okay. And I got that's 5.8 something here. Now, what about the simple method I use here? I got exactly the same answer. Yeah. Okay, so here's two different methods, but of course, they're consistent with each other. Yeah, so there you go. Two methods, same answer. Moving on. Number 13, wildlife. The initial population of rabbits in an area is 8,000, and the population grows continuously at 26% each year. Write an equation to represent the population after 2 years. How long will it take to reach 25,000? So, yeah, let's try a simple model of this. I think that would be more fitting. Um, so I'll say the population, here, let's just P for population equals the initial population times, let's just do simple growth, right? Something like that. Because they're saying 26% per year. So this R is 0.26. The initial population is 8,000. Okay? So population as a function of time is equal to 8,000 rabbits times 1.26 times, or to the power of however many years that passed. Yeah, it's good. Right, okay, so that was the first thing. Point. That was pretty good. Okay. Yeah, again, if you wanted to, like the last puzzle, I did solve it two different ways. You could force this into a continual growth equation with the base of e. This has base of 1.26. That's here. Okay. Oh, how long will it take to reach 25,000? So where the final population goes, let's put 25,000 rabbits here is equal to the initial 8,000 rabbits times the 1.26 to the t. Right? Since what we're solving for is in the exponent, you know a logarithm is going to pop up eventually. But first thing, let's divide over this 8,000. Okay. So it is 25 on 8. This is 3.125 is equal to 1.26 to the t. Okay. I'll go ahead and take natural log of both sides. So natural log of 3.125 is equal to, and then when I do it, see, I can take this t in front. Point. That's t we're solving for times natural log of 1.26. Okay. Last step is divide both sides by natural log of 1.26. So all I have to do is type this expression and that'll give me t. So t is equal to, what is natural log 3.125 over natural log 1.26? Looking at 4.93 years. Yeah, okay, that could be believable, right? Because that's approximately triple the population, isn't it? 8,000 to 25,000, about triple the population. Okay? It's growing at 26%. What is 1.26 to the power of, well, 4.9 is very close to 5. 5 is about triple the population. Yeah, it works. Or if I plug this in more precisely, 4.93. Yeah, we get okay, a little over triple. That looks right. Times 8,000 is 25,000. Yeah. All right. 18. Use models. The population of a city can be modeled by right, this function, where ft is the population 2 years after the year 2012. Based on the equation, what information do you know about the population of the city? And what year will the population reach? 500,000. Okay. So let's try this here. So 18, they're telling us the population as a function of time is, well, they say that, I'll call it PT. So 250, will this be, here, this is thousands of people. Okay, so that's the unit, thousands of people. And we're doing times e to the power of 0.01753, and then t for time. I don't know why I box that in. Or we'll have to solve that eventually. Okay. But what do we know? So right, I know that the initial population, okay, is equal to 250,000. Okay. What is the growth rate? Growth rate. Okay. Well, let's try this. Let's let 1 year go by. Like here, if I just focus on this and I say, so growth rate. Right. Let's let 1 year go by. Let's do e to the 0.01753. Okay. Here, and I'll show you guys how to get growth rate. Right. So e to the 0.01753. Right. Right. Now this is 1.01768. Okay. Now if you subtract 1, it tells you how much it's grown by. Okay. So the growth rate is equal to 0.01768, or roll the decimal a couple places, 1.768% per year. Okay. So this population is growing at 1.7 something percent every year. Okay. That's what's embedded in this superscript k value. In part B, we're looking for a population of 500,000. So 500, remember this is thousands of people, so it's called 500, that's 500,000 people. So 250,000 people. And then they gave us the rest of this. And then we're solving for t. Okay. Divide those sides by 250. 250, 250. Okay. Now this right here is equal to 2, isn't it? That's 2. Okay, so another way, they could have said, how long will it take for the population to double? Yeah. So we got 2 equals e to the something. With a t up here. Okay. Take natural log of both sides. And now I have natural log of 2 is equal to 0.01753t. Right, the t is no longer in a superscript. Now it's down on the same level as everybody else. Divide both sides by its coefficient, right, which we've done a ton of times, and I've got just enough space on the paper to write the answer. So you guys know I'm going to take natural log of 2. Here, I'll do it in fact, natural log of 2, close parenthesis. I'm going to divide down this coefficient right here. 0.01753. That looks like 39.5 years. Okay. So it takes between 39 and 40 years for the population to double, according to this model. There you go. Okay. And last one I'm covering with you guys here, number 20. Analyze reasoning. Explain mathematically why, okay, F it to here. Let me write down this, this function here. So this is number 20. We got f of t equals c over 1 plus 60 times e to the negative 0.5t. Okay. Approaches but never reaches the value of c as t approaches infinity. So we're talking about limits here. I'm going to write that word limits. Okay. When you take pre-calculus, they might start talking about limits maybe near the end of the year. At least that's how I used to teach it. And then when you get to calculus, like the beginning of calculus, they get the limits. So limits is like if, say, the time approaches value but never quite reaches it. They're sending t to infinity in this case. And the way you write that mathematically is right. LIM for limit, t, and then arrow infinity. So t approaches infinity. Of course, we're not actually going to like 100 trillion years from now, because the Earth is dust. But right, what's the mathematical limit of this function here? So c over 1 plus 60 times. Right? Now, here's the key: is that we do have a negative exponent. What is e to the negative infinity? Let me show you guys on Desmos, because there's a really nice graphical solution to this. Let's get oops, get that off. All right, let's get Desmos here. What is very simply e to the negative x, well, I should say y equals, let me go to that. Well, they gave it to us anyway, but you guys see what I'm going for. F of x equals or y equals. Okay, okay. Yeah. All right, so that looks like an exponential decay curve, but you guys see as you get further and further to the right, doesn't this asymptotically approach 0? It approaches 0, doesn't it? Right. So I think the limit would have to approach 0. Or you could try this on the calculator. T's going to infinity. So this is e to the negative 0.5t. Yeah. So if I do e to the negative, and then just type a big number, like 100, let's see what this says. E to the, oh, okay. So, well, why is it saying 3 point something? Because that's 10 to the negative 44. Yeah. It's just like 0.00000, like 40 something zeros before you even hit any digits. Okay? Let's try 200. Oh, I didn't even think that was going to show up on my calculator. 10 to the negative 87. Let's try 300. Yeah, at that point, it just kind of runs out. It's like, okay, it's pretty much approaching 0. So this part right here goes to 0. All right, trying to show you guys that. Okay. Well, if that's 0, 60 times 0 is 0. So the limit is equal to c over 1, or simply c. Okay, and that's what they wanted you guys to see. Okay. This looks like a logistics growth type equation. Here, I'm going to go ahead and plug this into Desmos for you guys. I'm going to speed this up. It shows up on the top of my screen because I do want you guys to see what this curve looks like. It's a pretty cool curve. You almost certainly see math classes in the future. Now for C here, I'm gonna make up a number for C. How about, how about 100? Let's do it. And then divide by, and then down here, let's do 1 plus 60 times e to the power of negative zero point 0.5, well, x, I'll call it, right? Like that. Okay. Now what you can see so far, well, it looks kind of like exponential growth, doesn't it? Like if you had an initial population of, whatever, right? Like if you plugged in 0 for x, I guess it simplifies to like 1.6 something. Okay, so it's gonna looks like it's growing exponentially, but if you zoom out, oh, look at that. Look at that. It actually levels out at the numerator value, which is exactly what we just proved right there, what we just showed. I said it's going to approach whatever C is. And for Desmos, I just typed in C as 100, and it levels off at 100. Yeah, oftentimes, realistically, in the wild, populations do this, right? You have a bunch of rabbits, right? And they start growing their population exponentially. Right? But then there's this resource limitation, right? There's only so much grass to eat or whatever, right? Or maybe they become so plentiful that now predators have more food to eat themselves, so now the predator population grows, right? And so there's this balance in nature. All right, so there you go. And um, that's a wrap on 8.6. No, sorry, 8.5. That's a wrap on 8.5.